Now onward to chapter 22, or electromagnetic waves, also known as kind of EM waves, kind of shorthand. What we'll kind of start off with is just kind of quantitatively talking about Maxwell's equations. It turns out they're kind of complex and take some calculus to get there, so I'll just talk to them briefly. Talk about how we can produce electromagnetic waves, again, EM waves. Light itself is electromagnetic waves. I'll talk about the electromagnetic spectrum, how we can measure the speed of light, and just a little bit about energy, radiation, pressure, and wireless communication. Now, Maxwell's equations actually comprise of 4 laws that we've already talked about. Gauss's law relating electric field to charge, a law stating that there's no magnetic monopoles, Faraday's law that says a changing magnetic field is going to produce an electric field, and lastly, one that's kind of new but not quite, Ampere's law. A magnetic field is going to be produced by an electric current. Kind of the addition is that it's going to be produced by a changing electric field, so I'm going to talk to that for a second. So let's just kind of take a look at Ampere's law. Remember that Ampere's law said that if I draw kind of a closed loop around a wire here, or a kind of a closed path, then I can say that the magnetic field multiplied by my path is simply going to be the current multiplied by is going to be mu naught permeability of free space multiplied by the current enclosed. And for this example right here, it works out quite nicely. Now, suppose I were to look at a capacitor. It's perfectly reasonable to put one of these guys in a circuit. If I were to kind of draw kind of a closed path right here, I'm not going to have any current enclosed. However, we are going to measure a magnetic field there. So it seems like Ampere's law isn't holding for a capacitor. But kind of what's going on here is, we're having charge build up on this capacitor, or it's actually discharging, but charge going away. So the charge is becoming smaller and smaller and smaller and smaller. So this is negative, it's becoming less negative. This plate is positive, it's becoming less positive. And so the electric field is actually changing. It's getting weaker. It's getting smaller and smaller and smaller and smaller. So it turns out that this changing electric field is just as good as having current flowing for an Amperian loop. So this is more or less why we take Ampere's law and says that a current carrying wire can produce a magnetic field, but also we can produce a magnetic field by a changing electric field. For example, plates of a capacitor. Now let's take this a little bit further and say, hey, how can we produce electromagnetic waves? Since a changing electric field is going to produce a magnetic field, and a changing magnetic field is going to produce an electric field, we can really create a wave that's going to propagate on its own. How do we do this? Well, we wiggle electrons. Suppose I've got an antenna and I've got an electron on it, and I say, hey, what direction does the electric field point? It's going to point in that direction right there. Now suppose some time later I've moved that electron up there. Now my electric field is going to point up here. Say, hey, now step 3, let me just move my electron down here. Now my electric field is going to point down, down right there. So now I have a changing electric field. This is going to produce a magnetic field. It's constantly changing, so it's going to produce a changing magnetic field. This changing magnetic field is going to produce an electric field. Now, what does this electric field look like? Suppose I'm, kind of having my electron wiggling it up and wiggling it down. Well, the electric field is initially going to point up, and then it's going to point down, and then it's going to point back up as I wiggle my electron up and down and up and down and up and down and back and forth. The magnetic field, there's a little bit of physics there, is going to be perpendicular to the electric field. Don't worry about that too much, but it is also going to be going up and going down and up and down, and actually the frequency of the magnetic field is going to be the same as the frequency of the electric field. The electric field and magnetic fields are going to be perpendicular to each other. It's also going to be perpendicular to the direction of propagation. So in this case right here, the wave is propagating in this direction. So I can kind of come back to this one and say, kind of draw my electric field. It's going to go up and down and up and down and up and down. I'm not going to try to draw my magnetic field because it's going to be too hard for me. And it's going to be moving in that direction. Now I'm going to have, say, a radio antenna just like that, this thing has free electrons on it. What's going to happen to this radio antenna is it's going to feel an electric field. That electric field is first going to go up, and then it's going to go down, then it's going to go up, and then it's going to go down. And so this electron is going to start to oscillate at the same frequency of the wave, which is actually going to be the same frequency that this electron is moving up and moving down at. Now, coming back to our electromagnetic wave here, everything that we learned in chapter 11 and 12 is going to apply to electromagnetic waves. So here we're kind of looking at the one full wavelength. The speed is going to be equal to the frequency multiplied by the wavelength. And we also have kind of concepts of amplitude. Now, Maxwell did some calculations. He played around with those four laws, and he actually calculated the speed at which this wave should propagate, at least in a vacuum. And what he found it was to be related to the permeability and permittivity of free space. And using what we know about those two values, we've seen those in the past couple of slides, found out that this is going to be the speed of light in a vacuum is going to be 3 times 10 to the 8th. So anytime you see a problem with an electromagnetic wave, pretty much in air or a vacuum, you're going to use 3 times 10 to the 8th. That's kind of something that you should know. And pretty much as I've already mentioned, light is a wave, and we know that it's going to be an electromagnetic wave. And so what we can do is we can say, hey, I remember that my speed is going to be equal to my wavelength multiplied by my frequency. Now I'm simply using the speed to be 3 times 10 to the 8th meters per second, as opposed to just some slower speed that we would use for mechanical waves. Now, I've said that these creatures called electromagnetic waves are essentially caused by wiggling electrons. So take an electron, wiggle it up, wiggle it down. The frequency with which you wiggle it up and down is going to be the frequency of the wave. So we can actually have a whole spectrum of electromagnetic waves, a whole lot of frequencies with which we can wiggle electrons up and down. We know that we have the speed is going to be equal to the wavelength multiplied by the frequency, and so we can pretty much convert from frequency to wavelength, knowing that the speed is always going to be 3 times 10 to the 8th. So kind of take a look at the increasing frequency right here. We have a whole bunch of different waves with different names associated with them. I got radio waves. Think about AM, FM radio. Or AM radio, FM radio, slightly different frequencies. Take your favorite radio station, say 105.5. You know the speed. You could calculate the wavelength. A little bit higher in frequency is going to be microwaves, as well as those the radar that you use to tell whether it's going to rain or not. Increase the frequency to infrared, which really means below red. This little sliver right here is the section that we can actually see in. So this is going to be the spectrum of visible light, going from about 400 or 700 nanometers down to 400 nanometers, and essentially doing the old Roy G. Biv, where red is going to be the low frequencies, violet's going to be the higher frequencies, ultraviolet above violet, X-rays and gamma rays. Something to kind of keep in mind, that as we go in this direction right there, the energy is actually going to increase. And kind of as you would expect, as we increase our frequency, you can kind of see that the wavelength is going to go down, because these two guys are going to depend inversely upon each other. I mentioned on a couple slides ago that C was equal to 3 times 10 to the 8th. However, as we've gotten more and more precise measurements of mu naught and epsilon naught, we've actually kind of refined this down to 2.9979 times 10 to the 8th meters per second. Really, if you're doing a calculation, using 3 times 10 to the 8th is going to be more than sufficient. Something else I forgot to mention on that particular slide, that Maxwell calculated at the speed of light to be related to the permittivity and permeability, is it's also going to be related to the ratio of the electric field to the magnetic field. So that can be kind of useful when we're, say, calculating maximum values of electric field and magnetic field. Now we know that waves can transmit energy. I showed on one of the first couple of slides that we can wiggle an electron on one antenna and make another electron wiggle. So how much energy is stored in each field? We can write the total energy of a wave to be the sum of the electric plus the magnetic. It turns out that each field is going to contribute half to the total energy density. So we can kind of write it like this. And then we can use this relationship right here to say, hey, what if I wanted to write this just in the language of the electric field? So I can calculate my magnetic field in the language of the electric field, kind of stuff that in right here, and say that the total energy density is going to be the permeability of free space multiplied by the electric field squared. And just to kind of summarize for chapter 21, note that I added a little bit of an equation here that you'll probably find useful.